I think we have 29 participants so far. So hopefully everyone can hear me. If not, please let me know. So hi everyone, bonjour à tous. My name is Ryan Kilpatrick. I'm a research engineer at Cabinet Energy Ottawa, a federal laboratory within Natural Resources Canada. And I'm pleased to be moderating the second session of the Canadian Wind Energy Research Network today. We begin today on a somber note. We've learned that professor and wind energy researcher Christian Masson has recently passed away. So I would like to start by turning it over to Lu-Chen Chang, who will say a few words.
Thank you. It was with great sadness that yesterday we received the message that Chris Masson passed away. He was only 57. He was a professor at ETS, working on wind energy for many years and made significant contributions to the technical advancement in Canada. He was the CRC chair and was the leader of Theme 2 of WestNet. I had a great privilege to work with Christian. Rest in peace, Christian. We will miss you.
Thanks, Lu-Chen. So for today's session, just a bit of background for today's section. There are currently 18 or 19 active research tasks in the International Energy Agency IEA Wind Technology Collaboration Program. Canada participates in 9 of those tasks. So today we will see presentations from Canadian representatives on 3 of those tasks, and the others will be presented at the other webinar sessions this week or next week. And then today, following the 3 IEA task presentations, we'll see presentations from researchers on numerical modeling, both at the wind turbine and wind farm scale. And then we'll close with 3 presentations on wind turbine aerodynamics. So it should be a good mix of different topics today. So just from a high level, just to remind everyone of the goals of the research network. If you weren't able to attend the first presentation, the opening day, there should be a recording available. But the goals are to share current and planned research activities that are occurring within your organizations and to raise awareness of those, as well as to identify research gaps, intersecting areas of interest and potential opportunities for joint research and for forming collaborations. And so in terms of next steps, after this round of 6 webinars occurring over the next couple of weeks, we'll have a follow-up webinar probably in a couple of months timeline to talk about funding opportunities and to get feedback from industry. So please stay tuned for that. Just some general housekeeping items for today. Speakers, please aim to limit yourselves to 5 minutes. I believe we will be giving an indication when you are close to or at the 5-minute mark, and then please try to wrap up shortly thereafter to leave time for a discussion. Generally, please mute yourselves when not speaking. And if I could just ask everyone to hold your questions until the discussion period or to write them in the chat, and I'll bring them up one by one in the discussion. So with that, let's get started. And the first presentation today is by Jamie Baxter from University of Western Ontario on task 28, social acceptance of wind energy. If you're, I'm not able to hear you, Jamie, if you're speaking.
I am.
So we had you for a moment. There was a lot of echo though. So could I just ask everyone again to mute yourselves if you're not speaking? Okay, so it sounds like Jamie may not be here yet. So unless I hear otherwise, let's move on for now to the second presentation, which will be by Marc Desfossés from Nergica on task 32. We can come back to Jamie in a moment.
Thank you. Hi, everyone. My name is Marc Desfossés, and I am a project manager at Nergica. Actually, I will probably need less than 5 minutes for my slide. So, the operating agent of IEA Wind Tasks 32 is currently Henry Clifton from the University of Stuttgart. In brief, task 32 aims to identify the main barriers that exist to the use of LiDAR for wind energy applications. This includes a broad range of activities like site assessment, power performance, load control, and complex flows. These activities have been separated into several groups, which are listed hereafter. The first group, the group Wind LiDAR in complex terrain, is about looking into academic and commercial applications, like scanning LiDAR in commercial projects, or scanning LiDAR for the whole wind park instead of flow modeling. I am gradually taking the lead of the group Wind LiDAR in cold climates from Nicolas Jolin. This group tries to find correlations between LiDAR data availability and meteorological conditions like icing or the lack of particulate in clean air. In order to understand the latter, we need some knowledge of aerosol physics. The goal of the group floating LiDAR systems is to achieve an uncertainty lower than 2% in the measurements, so that LiDAR can be an acceptable source of wind speed, direction, and turbulence. The group turbulence intensity tries to better define turbulence through LiDAR applications. An important challenge is how to define turbulence. That is, do we use the mean and standard deviation, or do we look for a better suited method? The group LiDAR assisted control tries to design LiDARs for control applications, which involves certification and some engineering. And the group forecasting uses numerical weather prediction models, which use LiDAR data to improve their performance, their goal being to optimize the wind farm control. And finally, the group collaboration on wind LiDAR hardware and software tries to define standards, because there may exist different interpretations of the same LiDAR data. Okay, thank you for your attention.
Okay, thanks very much, Marc. So we'll go now to Sergio Gualteras, also from Nergica on task 41. Are you there, Sergio?
Yeah, can you hear me?
Yes, go ahead.
Perfect. So yeah, this is Sergio Gualteras, project manager at Nergica, representative to task 41 of the International Energy Agency, starting in 2018. So first of all, a short definition of what distributed wind is. In the group, we agreed on 4 use cases for defining distributed wind that you can see in the schematic. So first of all, behind the meter wind turbines, which are installed by residential, small businesses, farms, and commercial and industrial customers, mainly. After that, wind power on grid-connected microgrids, so ranging from small microgrids for small applications that can interact with the grid, and going up to small communities and defense or military bases. Third use case will be wind power connected to distribution grid, ranging typically from 1 megawatt up to 20 megawatts, providing energy to the grid, but also providing ancillary services as voltage and frequency regulation. So these three use cases interacting with the distribution grid. And the fourth use case, which is wind turbines in isolated grids, depending on the isolated grid, it can be interacting with other energy sources and storage systems. And in our case in Canada, mainly driven by diesel based generation. So this is for the definition. It's clear that the definition is not the same depending on the country, but we establish a framework for working into that. The main goals of the activities of the task are to coordinate international distributed wind energy research, facilitate collaboration on several research topics that I'll explain later in the presentation, and then increase the visibility of wind technology as a distributed energy source. We've seen, for example, in 2020, several reports talking about the role of renewables in the upcoming years, and mostly talking about solar and the role of solar in this energy transition. But we are willing to inform those studies and this kind of publication as to show what the value of distributed wind can be, and also to show the advantages of combining solar and distributed wind. Regarding the work packages, we have 5 work packages we are working on. First of all, standards. So research to support development of design and testing guidelines for small and mid-sized wind turbines. This is recognized for several members and industry players to be a big barrier for wind turbine development. And we are working on that, mostly collaborating with NREL. They are updating the IEA standard for small and mid-sized wind turbines, and we are preparing an update for the 61400-2 standard. Professor David Wood has been working on that actively. Data catalog, we are assembling a catalog with metadata for data sets that can be shared with among members. If you have any data that you can share, even commercial use, please do not hesitate to contact me. After that, integration. So integrating distributed wind to the grid. This is an important matter to us. Advanced controls and integrating also ancillary services. Outreach and collaboration for collaborating with other tasks, particularly 19 and 32, and innovation and downscaling, trying to reproduce innovations done to utility scale turbines to mid-size and small wind turbines. So that's about it.
Okay, perfect. Thanks very much, Sergio. So we'll move along to Arjun AJ, a PhD student from UBC Okanagan. Go ahead, Arjun.
Hi everyone, my name is Arjun Ajay. I'm a PhD student at the Computational Fluid Dynamics Lab at UBC Okanagan under Professor Joshua Brinkerhoff. So I'll be presenting on the topic of LEA simulation of flow over wind turbines in complex terrains. Uh, Modeling of wind farms in complex terrains is gaining in importance because of the lack of optimal locations for deployment of large wind farms. So complex terrains can be a combination of terrain topology as well as the surface roughness effects, as can be seen in this image. So it's important to understand the effect of the terrain on the downstream wake growth, as well as what effect it can have on the upstream blockage effect of the wind farms. For example, the wake produced by the terrain can interact with the turbine wake, and this interaction need not be necessarily linear. And also, the terrain can lead to an adverse pressure gradient upstream, which can increase the blockage produced. So in this study, we used a numerical model that's based on large area simulation to model the neutral atmospheric boundary layer flow. So we have used what is called a precursor successor method, where during the precursor simulation, you do not model the turbine or the terrain, but just the flow. And you want to develop the fully developed flow, which is used as inlet condition for the successor simulation, in which both the terrain as well as the wind turbine is included. So in this study, which we performed, the complex terrain is a Gaussian hill, which has been modeled using a sharp interface immerse boundary method. And for the wind turbine, we've used actuator disk model to model the body force due to the wind turbine. Next slide, please. So these are the modeling parameters that we have used in this initial study. So it's based on a experimental size domain. So the streamwise length is only 3 meters, the spanwise 1.5 meters, and the vertical height is 0.7 meters. Since it's a preliminary study, we have already, used a coarse grid with 150 cells in the streamwise, 100 in the spanwise, and 100 in the vertical direction. The velocity at hub height is 8 meters per second, and the hub height is 60 millimeter, and the turbine diameter is 45 millimeter. The Gaussian surface reduces to 0.01 turbine diameters within 13 turbine diameters. So it's a fairly gentle slope which we used for this study, which is based on a paper by Professor Antonio Segalini. Next slide, please. So I'll come to the initial results which we have obtained. So we have run like 2 cases, where the initial one is with just the hill, and the next one which includes both the hill as well as the turbine. So you can see that in the streamwise mean velocity plot, which has been plotted at the middle of the domain, there is a speed up observed at the crest of the hill. And you can see a velocity deficit within the hill wake, but the velocity deficit is not as pronounced, and this is because of the gentle slope, so there's not as much flow separation. So the velocity the deficit in the wake is not as pronounced. If you look at the spanwise mean velocity at a surface which is a 0.75 turbine diameter, we can clearly see the increase in the spanwise velocity as the flow tries to divert around the hill. So depending upon the position of the turbine on the hill, these profiles can have an impact on the incoming flow as well as how the wake is developed. For example, in this second case, which shows the hill plus turbine, the turbine has been placed at the hill crest, so it'll benefit from the speed up that is observed at the hill crest. We'll be running additional test studies where we place the hill at multiple positions around the hill, as well as look to compare how placing it at different positions affects the incoming upstream flow and how that affects the blockage upstream. So these are just the preliminary results, and yes, we look to perform more studies and explain to you how the results will be in the future. Thank you.
Thanks very much, Arjun. I'll just pause here and ask if Jamie Baxter is on the line. Okay, not hearing anything yet, so we'll come back to him at the end. So let's continue with David Kefti from Dalhousie University.
Great. I hope everyone can hear me. Yeah, my name is David Kefti. I'm a master's student working in the Renewable Energy Storage Lab at Dalhousie University with doctors Lucas Swan and Nat Puri. And research I'm looking at is the impact of various metrics on the capacity value of wind farms in Nova Scotia. Today, I'll be discussing the results for two of these metrics analyzed, the wind farm maintenance and data resolution. So we used the cumulative frequency analysis method for calculating the capacity value, which defines capacity value as the reliable production during high load times. So first, the data was adjusted to accommodate the metric being investigated. Then the high load times were isolated, and we calculated the 10th percentile production during these high load times. On the left side of the graph of the slide is a plot showing the capacity values across different wind farms. The data was used from Nova Scotia Power-owned wind farms, South Canoe, Sable, Nutby Mountain, and Glendew, and then one additional wind farm not operated by Nova Scotia Power. And the non-Nova Scotia Power-owned wind farm tried an alternative maintenance strategy in which they only performed maintenance on the wind turbines during periods of typically low load, guaranteeing the operability of wind turbines when the load was high and the electricity generated would be more useful. So on the x-axis of this plot, you can see the load threshold. Rather than picking a single point to consider high load, we gradually narrowed in on the peak in order to see how the wind farms behave at a range of high loads. And on the y-axis reads the 10th percentile production as a percentage of rated capacity, which allows for easy comparison between each wind farm. The higher they are at any given load threshold, the more reliable the production achieved during these high load times. As you can see, the orange line, which indicates the wind farm using the alternative maintenance strategy, is not higher than the other wind farms, which indicates that there is not a perceivable impact to the capacity value when using this alternate maintenance strategy. This means that aspects such as siting location and diversity have a greater impact on the capacity value than this maintenance strategy, which is also confirmed by the black line, which represents the aggregate of all the wind farms across Nova Scotia, which is clearly higher than any individual wind farm, as sort of a diversity of sources results in a reduction in the variability of the output. And then on the right graph, we determined how the resolution of the data impacted the capacity value. So data from wind farms can be acquired in various different resolutions. So typically we had data coming in at 2 minutes and 10 minutes, but it can also be acquired at hourly intervals depending on your source. So we just wanted to see how different resolutions could impact the capacity value. And we did this by starting with a 2-minute resolution and artificially reducing the resolution to 10-minute, 30-minute, and 60-minute intervals, and using the same method to calculate the capacity value as we did on the left graph. But as you can see, there's a fairly insignificant difference between each of the wind farms, or sorry, each of the data sets. So clearly there doesn't seem to be much of a difference between different resolutions. So thank you. And I guess if you have any questions, save them for the end.
Thanks very much, David. So let's keep moving. And next up, we have David Wood from University of Calgary on unsteady behavior of smart airfoils.
Okay, thank you, Ryan. Can you hear me okay?
Yes, we can.
Okay. Yes, I'm going to talk very briefly about a lot of work that we've done over the last few years and continuing to do on the unsteady behavior of smart airfoils. And by smart airfoils, I mean airfoils that either have a trailing edge flap, as you can see on the bottom left of the slide there, or airfoils that are fitted with vortex generators, or a combination of the two, which we've looked at both as well. And the typical way in which these smart airfoils are studied is by making wind tunnel models of the airfoils and testing them in a wind tunnel with the foil sinusoidally pitched. So the airfoil model is pitching as shown by the red arrows there, and we measure directly the unsteady loads acting on the airfoil, either in terms of the lift and the drag, or the chord-wise force, that is the force along the direction of the chord, and the chord normal force. In addition, we have done a lot of particle image velocimetry measurements of the flow to get a better idea of what these complex flows look like. And going back to the first point that I've got here, unsteady lift and drag are much more complex than the steady forces. The magnitudes of the unsteady forces can be very large, and so we need to have accurate models of this unsteady performance for things like real-time control of wind turbines, because generally speaking, if you look in the research literature for wind turbine control, the control algorithms or the theory behind the control is usually much, much more complex than that of the aerodynamics. Now, I don't have time in this presentation to go through all the data that I have. I've put it in this presentation in 5 slides so that people can look at it afterwards. So what I would like to do now is skip the next slide and go to my third one, please. Yeah, skip this one. Okay, so this is a slide that shows what happens when you use the trailing edge flap that you can see at the top of the diagram here to control the loads during the pitching of the airfoil. I haven't got time to go into the details, but you can see by the numbers in the figures in the middle of the slide that significant reductions in the unsteady loads are achievable through control by the flap. And on the right-hand side, again, very briefly, you can see some of the results of our particle image velocimetry measurements of the flow as this flapped airfoil, this smart airfoil, is being pitched. And you can see, get a pretty good indication of how complex that flow is. So can I skip the next slide as well, please? Skip that one and go on to the last bit here. Oops, gone one too far. Okay, what we intend to do with this work is to adapt and extend an interesting line of analysis that we've just published, the references at the bottom of the slide here, as references to some of the other work on the previous slide. We've used the technique called impulse analysis, which we have done for steady flow, and that has just been published. And we're going to apply it to unsteady flow. This has some very attractive options to it because the impulse version of the unsteady equations is much simpler than the conventional version of the equations. From that, we intend to develop a generic blade element model to apply to wind turbine blades when they change their pitch. So this is the top of the power curve as the power has to be limited. And we want to combine this with a control strategy to minimize the unsteady load during that pitching. And I've been told that I've just about run out of time, so I'll finish there. So thank you for listening.
Thanks very much, David. Excellent use of time, a lot of information there. Let's go to David Johnson now at University of Waterloo. And I think you can share your own, you want to share your own screen, right, David?
Yeah, can you hear me now?
Yes.
Okay, let me just, I'm not sure exactly what you can see here.
Can't see anything at the moment.
See something now?
No, I can't.
Just
oh. Yeah, I think we've got it there. Yeah.
Okay, great. So I appreciate David Wood giving a little introduction to, so we do some similar and comparative work, so that's good to know. What I decided to do was a little more general background because some of the people, or many of the people in our kind of audience here maybe don't know the past of our WestNet group. And our group does mostly aerodynamics and acoustics of wind turbines. And we have, for the past some time, I guess we built this facility in 1999, 2000, and it's really a large scale test facility for us to do lots of many large scale aerodynamic tests, but predominantly what I do, of course, is wind energy and wind turbine testing. So of course, this facility is a national, from CFI, national funded project, and we welcome people to come and do testing and so on in this facility. We've built numerous wind turbines to evaluate different aspects depending on what we're interested in. Typical diameter, our facility is very, very large. It's about 20 meters long, just to give you an idea of the scale. And we developed numerous turbines which are fully instrumented to scaled replicas of the size of what we would see in a large megawatt scale situation. We also have a field turbine, and this turbine has been also instrumented by us. And we've done things like instrumented the blades and looking at the blade deflection, blade erosion. And this particular slide is showing a tuft visualization, which we then look into with image analysis and try to predict what the actual stall characteristics are of the blade under operating conditions. And we have some videos on YouTube, which actually make people quite dizzy because the camera is attached to the wind turbine blade, as you can see here, and as it travels around, people get a little dizzy. So most of the comments on our YouTube are about getting dizzy, not about wind turbines. So we have that capability as well. We've done lots of projects over the last number of years, some for industry, some for research purposes. And I just highlight things like winglets and vortex generators we've done in the past. And here's just an example of the type of winglets we've had a look at. And the bottom slide plot is showing you the power augmentation for winglets. And in fact, winglets are very tough things to design because they can augment the power in certain flow rates, certain wind speeds, but they can actually have a detrimental effect. So you have to be very careful when you're designing a winglet. And the more recent work we've done is, with trailing edge flaps, a bit like what David Wood was just talking about, where we've had a computerized smart blade, which we've used to test pitching control versus trailing edge flap. For load reduction, we found there's quite a significant advantage to trailing edge flaps. And we're kind of looking for the next step of that to implement that. So we've done a lot of testing on in our large facility, but the next step will obviously be to go and take that to the field with either our turbine or with a industry partner. And this is just a photograph of, we've done a lot of field studies as well. This is taken from a project wind farm on the Lake Huron shore, where we're doing some image analysis for blade erosion and blade monitoring. So not particularly aerodynamics specialized, but use some of the resources that we already have. So as I said before, we have some great test facilities. This COVID thing has sort of slowed down a lot of their experimental activity due to the large scale nature of what we do. But of course, we're looking for interaction with others. And most of the people we do work with are, of course, European researchers, a lot of connections there. And I think I'm almost out of time. And I guess we've also done an applied project at a remote community, and there was some mention of that earlier on in the conversation. We can talk maybe a bit more about our strategy for that aspect. So at this stage, I'd like to stop and turn it over to you, Ryan.
Okay, thanks very much, David. So our last presenter for the day, if we don't hear from Jamie, is going to be Rad Heggie from the University of Victoria. We'll get your slides back up there.
Okay. Okay, good. Good morning and good afternoon, everyone. I'm Rad, and I'm a PhD student at the University of Victoria under supervision of Dr. Crawford. Today, I'm going to talk about something quite different from what we talked about till now. It's more going into detail of numerical simulation of the wind turbines. So I would start with why we actually run the simulation. We run the simulation to really understand what are the loads that are going to be applied on a wind turbine in real field. Based on the standards that we have to take a couple of random seeds from a wind spectrum, wind field spectrum, make wind speed fields, and then run them through the commercial wind turbine elastic codes. The output of that commercial elastic load is the output of commercial elastic calculator or code is the loads or the power. And then we look at the statistics and we say, okay, this is the extreme load, this is the fatigue load, and we can go further. It is the way that you do that in commercial world. This is one way. The problem with this way is you have a limited resources to run your simulations, and you choose from the random field, you choose a limited number of seats. As a result, the output is not a converged statistics. From that bad statistics, we extract extreme loads, we extract fatigue loads, or we look at other aspects. Because we don't have complete picture in terms of the statistics, we have to apply safety factors. What we are proposing here is looking at things in our way. So what we are proposing here is going through an array, which is the green boxes in this flow chart. We start with looking at the wind field. So we generate the wind field. It's a cheap part to make. It's very cheap to generate many wind fields and many wind speed via TurbSim or any other unsteady wind generator. Then we try to, oh, I forgot to say something. When you make this wind field, one of the challenges that we face with is the number of random variables that you have. This number of random variables is something that you cannot really control, and it should be there in order to really generate the randomness, the unsteadiness in your wind field. What we're proposing here is taking that wind field and then taking it through some data reduction methods, which here what we propose is proper orthogonal decomposition. Then, because we do that, then we can have a control on the randomness that we put in. We can have the control on the random number that we put in. Then we can pass through that reduced wind field into elastic code by doing a smart sampling from the random domain and random numbers, and running that reduced wind field through the elastic code. We can build a surrogate model in a non-intrusive way on the result. What is the usage of surrogate model? Surrogate model is a statistical model of deterministic simulations. It means it can cover a larger and wider map of our input to the output. So, and also it is very cheap to run. So by having that surrogate model and taking that surrogate model through the Monte Carlo simulation, we can run it many times, enormous amount of times. And then the output, which is again the loads or the power, it is going to have a convergent statistics. Therefore, we can look at things and say, oh, we have a fat tail. Oh, or we are taking too much safety factor into account. Maybe we can reduce that one. Or maybe we are conservative, or maybe we are not conservative enough. Yeah, so that is what we are doing, and that is my PhD research. Thank you. Thanks for your attention.
Okay, thanks very much, Rad. So that brings us to the end of our scheduled presentations, unless anyone has heard of from Jamie. But if not, I propose we move into the discussion phase. So please feel free to unmute yourselves and ask questions, or write them in the chat and I will bring them up. But let me just check if we have any questions here.
I have a question on the Dalhousie work with the capacity factor, and just wondering kind of the, I guess the statistical nature of that. Was that kind of a year's worth of data you were working off of, or kind of, yeah, interested to hear a bit more there.
Yeah, so I'm unmuted. I think everyone can hear me. So the, yeah, it was 3 years of data. It was from 2017 to 2020. Yeah, I think I must have forgotten to mention that, because it was definitely something I meant to specify. But yeah, so thanks for bringing that up.
I may have totally missed it too.
No, I probably forgot. Thank you.
Sorry, I had a question for either David Wood or David Johnson. Maybe you could give a little bit of a high-level description, like how common are smart airfoils generally in commercial applications, and what are some of the barriers to more widespread adoption?
David, did you want to have first go at this? Maybe it's not there, so I'll have first go. It's David Wood here. I mean, vortex generators are commonly retrofitted to wind turbine blades now. There's a company, is it called Smartfoil or something like that in Germany that makes vortex generators that have been fitted to turbines in North America. I've had discussions with people at TransAlta about using vortex generators on their turbines. That's a fairly simple thing to do, because that's a passive change to the turbine. You just glue the vortex generators on, presumably when you're repairing the leading edge of your blades for erosion. Flaps I think have been tried on a number of test turbines, but as far as I know, there's no commercial application of them yet.
So yes, I would concur with what David said. You can purchase vortex generators. Some of my students who work for Siemens in Europe will sell them to you, but I don't think there's a really strong consensus on value, definite value added for these devices. Is that fair, David? I don't know.
I think so. It's one of those issues where it's like a little bit like winglets on aircraft. The purported improvement in performance is around 1 or 2%, which is pretty close to the noise level with which you are stuck with when you do the measurements of power output or whatever. Yeah.
Okay, thank you.
Karen's asked an interesting question about turbuncles or turbicles. I think that there's been a lot of research on these things generally and their effects on airfoil performance. Again, it's a little bit like what we were just saying about winglets and vortex generators. I don't think there's a significant documented value to having them. And something like the turbicles or turbuncles, they require major changes to the blade shape. And so I think you'd have to be able to demonstrate a major change to the performance before it would be likely that a blade manufacturer would change their molds to make blades of that shape.
I would agree with that turbicles statement for sure. There's a lot of hype and not a lot of data. I think that would be how that's portrayed.
Okay.
My personal take on all these things is that the value is at the interaction between the aerodynamic modifications and the control. I think if we could get that right, I think we would make a lot more progress than by looking at them independently.
That makes sense.
I have a question. If am I okay to ask a question or?
Go ahead.
Yeah, so I have a question about the flap one. How much do you think that flap is realistic in real world? I mean, how much do you think in commercial world they're going to adapt the flap to the blades in order to extract more energy?
Okay, so, oh, sorry, David, I'll kick off. So I would say the main goal of the flap is not to extract more energy. The main goal of the flap, in my mind, would be to reduce load fluctuation, or try to, which means you have to have a fairly active flap in order to be able to activate it in the time frames of the dynamic loads that you are experiencing. But some of our cases, well, we've done some, I mean, it's on a turbine, but it's in a controlled wind facility, and we've shown some pretty significant load reduction for using a flap, but again, it's not a field condition and so on. So it's in the orders of 25% reduction in load fluctuation, which if we even come close to that, that's a pretty significant advantage for the drivetrain of the turbine. David, sorry, jump in.
No, I jumped in on you earlier, David, so we're I don't really have anything to add to David's comments. It's spot on. The only thing would be that it's not a trivial test, not a trivial thing to do to make a 100-meter long wind turbine blade with a significant length of flap. And that's, I think, partly why the idea of morphing airfoil sections has come up as well, but I don't think there's much value in that either, from what I can see.
Thank you.
There was a question in the chat to follow on about the swept rotor nose cone, similar to the one being developed by the Canadian startup Biome Renewables. Does anyone, I believe the purpose is to reduce root pressure loss at the hub. Does anyone have any comments on that? or is able to talk about that technology in particular?
I don't know the technology in detail, but if you look at the distribution of power production along a wind turbine blade, it's dominated by the outer 30%. So whatever you do in the hub region is not going to have much effect. That's one of the reasons I'm somewhat skeptical about the use of vortex generators on wind turbine blades as they are being installed at the moment, because they typically are installed in the hub region. Now that makes sense in terms of trying to prevent separation on the part of the blade with high angles of attack, but it's hard to see that there's any significant power gain by doing that. But I'm not familiar with the technology, so I would leave my comments at that general level.
Okay, thank you. My understanding was that they're beginning to do field tests, and we might see some more results soon, notwithstanding the COVID delays. There was another comment from Tom Levy regarding the capacity value. Is someone from DAL able to comment on that? Do you want me to read the question, or can you see it?
I can see it. So the question seems to be about other impacts that having a higher resolution would provide to sort of the wind turbine. And I guess sort of my response to that is more that I didn't look too closely at other impacts that different resolutions would have. It was mostly focused on the capacity value because it was more of a broader question about different metrics or different impacts to capacity value rather than different things that one sort of the one specific impact would have on a broader sense. Because I guess sort of the way that the resolution was looked at from the analysis was more of the recording and storage of the data rather than the resolution. The data was sort of reviewed by the controller. Yeah, so I didn't get a chance to look at things like matching ramp rate or dispatch instruction, but I think at any point higher resolution is going to result in a better accuracy overall. At least what I found for at least capacity value was that the impact was small, but there did appear to be, some difference, but it was fairly negligible.
Thanks, David. There's a question from Sebastiano for the group working on load alleviation through flaps. Did you make some studies or comparison with movable or rotating tips of the blades?
I'll jump in ahead of you, David Johnson. The key thing with a flap is that it is small relative to the chord of the blade, and therefore the energy and time scales of its activation are likely to be much more useful than, say, doing something like moving part of the whole blade at the tip. So I think the focus on flaps rather than a section of the blade that moves is likely to be get more benefit, but I might have misinterpreted your question, but that's what I think.
Yeah, can we clarify what the rotating tips of the blade scenario is? Sebastiano, can you?
Yes. Yeah, because in the past I made some like simulations with adapting fast code for allowing for a rotating tip, like the last portion of the blade completely rotating, because that was for like it was a completely different purpose, which was like wake deficit decrease, and to increase the power production. We were studying control techniques with moving tips or pitching the blades to increase the power production of the downstream machines, so reducing the wake deficit. But I was thinking about this like possibility for the load alleviation also. The problem that we found was that obviously the aerodynamic loads goes to zero at the end of the blade, at the tip of the blade. So you have to have a quite big portion of the tip moving if you want some effect. So yeah, maybe I agree with you that the flap is maybe you can locate it in a portion of the blade where you have more effective, let's say, more effects on the loads.
Sure, just to go with what David Wood said there, we're looking at primarily targeting the high power production section of the blade, kind of centered on the 70-75% maybe range of the blade. The tips are hard to get in control, and of course the hub is, like as I said before, the hub's not really contributing any power at all, so I'm not sure why people would focus on that particular area.
Yeah, okay, thanks.
I had a question for Arjun when it comes to complex terrain. One of the common motivations for studying wind flow over complex terrain for wind energy applications is that it potentially increases the number of viable sites for wind turbine and wind farm location for siting. When it comes to the Canadian context, should we be looking at, or are you considering looking at specific terrains in Canada? And should we be looking at archetypes of Canadian terrain that are maybe worthwhile studying when it comes to looking at future capacity expansion of onshore wind?
All right, so since this has been a numerical study, we haven't specifically looked at different sites or places where this application would be specific to Canada. So at this moment, I cannot clearly answer on that question. But yeah, in the future, we would be looking at specific sites related to Canada to see how the study can be applied over there.
Perfect, thanks. Yeah, I know there's work going on in Europe, for example, but maybe a different situation where they're literally running out of space on flat terrain. But that's certainly an active area of research. So thank you.
Ryan, if you don't mind, this is Joshua Brinkerhoff. Can I also address that question?
Absolutely.
So the motivation behind Arjun's work, which is being supervised by me, is to improve site assessment tools. And particularly the question that our industrial collaborator is asking us to address is the upstream slowdown of the wind speed due to the blockage created by the rotor, or more generally the array of rotors. And so that's the main motivation, so-called induction effect or blockage effect. And we wanted to understand mechanistically that induction and what creates it and how to model it more accurately. And then to understand the impact of terrain on those. And in addition, the impact of neutral or non-neutral atmospheric stability. And so with respect to, should it be, would it be beneficial to generate a kind of general archetype of different terrain features? I think that would be worthwhile, because the site assessment tool needs to have some generality to be used for siting and making assessments beforehand in a range of terrains. And so I think that would be worthwhile. But as far as the immediate application, it's more focused on kind of understanding induction and understanding wake recovery downstream of large farms. And then the terrain effects is also going to be relevant as well. So that's kind of the two-pronged approach that we're taking to understand the mechanisms behind the induction and being able to predict them, for a range of atmospheric conditions, and then also adding on the complex terrain as well later on.
Okay, thank you. And so does your work also feed into understanding like the effects of terrain on loads that the turbine experiences, and or the effect of non-Gaussian wind flows, or like on fatigue, anything like that?
That probably could come in later, but that's not immediately our focus. The main focus right now is just understanding the actual oncoming wind, the induction or the blockage generated, and then also understanding wake-wake interactions downstream of farms and the interaction of one farm's wake on the downstream farm. So we can generate very long farm wakes, particularly under different stability conditions. And so those interactions are the focus.
Perfect, thank you.
Ryan, can I add a little bit to the discussion about complex terrain? Because in Alberta, we have an unusual feature of complex terrain, and our complex terrain is all upwind complexity, because all our strong winds in southern Alberta come over the Rocky Mountains. And that has a lot of interesting impacts. And one of the ones that we're studying is, what does that mean for the intermittency of aggregate power production? And how do you make a decision, for example, if you're wanting to put in a new wind farm in Alberta? If you follow the history, you go to a little region between or in southern Alberta that has about 90% of the wind farms in Alberta, because that's where the strong winds are. But we have incredibly intermittent wind power production in Alberta. So there's got to be an advantage in going somewhere else in Alberta, maybe to a lower wind resource region, but to a region where the wind resource is not correlated or is anti-correlated with that in southern Alberta. You know, so there's a whole range of really interesting issues of complex terrain that are not necessarily just about what happens as the wind goes through the turbines and hits the turbines downwind of those.
Yeah, that's very interesting, and certainly feeds into the correlations and capacity value questions that are being looked at by the researchers at DAL for the Maritimes. Okay, any other questions from the group? Okay. Well,
hey Ryan, can I ask or at least comment on something quickly?
Yes, please.
Just to say, well, first of all, the very interesting discussion, and I think where it's leading is certainly capturing my imagination a little bit more. So even the talk of modeling some specific terrain features in Canada, it feels like we're getting to that point where we know where we want to expand the grid, we know where the major load centers are, and therefore the geography around that is known. And so I understand the desire to generalize for a tool, but I don't know, I'm just thinking about specific landforms, whether it is Okanagan Valley or Tumbler Ridge area or Cowley Ridge, or these land features that we know about. So that's, yeah, just one thing. Very interested to see where research goes there. And then also this whole idea of the integration of the system, of the network. So you've got, like David was saying, this intermittent wind, because it's all concentrated in a certain geographic location. What about Saskatchewan and how they respond to the wind that is coming across Alberta, and sharing that data, that forecasting knowledge that moves its way across the country? Is certainly no expert in that area, but it seems to me that there's more that can be done with the system as a whole in the known geography that we have. Canada is not going to change its landmass significantly in the time that we need to go net zero. So yeah, just my 2 cents on some of these topics.
Thanks, Phil. Yes, certainly some interesting things happening at like the larger wind farm level when we get into wake steering and looking at kind of coordinated turbine approaches for the benefit of the entire wind farm. So certainly an interesting research direction. And interactions between multiple firms as well is certainly becoming a bigger issue in areas where wind farms are more densely co-located. Okay, any other discussion points or questions? So not seeing anything. So I propose that we wrap up this webinar here. Just a couple of reminders. Throughout the sessions, please feel free to provide feedback to myself or to any of the members of the steering committee or to Marianne and her team at WeCan about how we can improve these webinars and what type of features you would like to see or different formats that we can consider for future future sessions. We want to provide as much value as possible to you, the participants and the members. So please let us know. And a reminder that the next webinar will be this Friday, March 26th at the same time, 12:30 Eastern, 1:30 Atlantic. With that, I would just like to sincerely thank the presenters and all of the attendees, and hope to see you at the next one.
Thanks, Ryan.
Hey, everyone.
Nicely done. Good job.
Thank you. Thank you. Have a good day.
Thanks, everyone. Bye-bye.
Bye. Thank you.
Thank you.